Coming up on this episode of Coffee Literature Review, we talk to some scientists at the UC Davis Coffee Center about how roast profiles determine the amount of acid that you can get out of your coffee beans.
I'm sorry. That was a highly recommended. That is considered one of the finest espressos in the world. What is going on here?
We're back with episode 3. In the room with Willie. He's 3 months and about 15 days old. Doran here. Myself, Chris Hendon.
We have a record p-value.
Today we're doing something a little different. We've invited the authors of a recently published article titled The Effect of Roast Profiles on the Dynamics of Titratable Acidity During Coffee Roasting. It was published in Scientific Reports. This is out of the UC Davis Coffee Center. We're going to be speaking with Professor Irwin Donis and his graduate student, soon-to-be doctor, Laudia Anokye Bempah. We're very grateful to have them here. Thank you very much for joining us.
Hey, Chris, nice to see you, man. Look at that collection of whiskey you have over there in the back.
Nice to see you too. You know, I didn't realize it was you till this morning. I saw your picture on your email and I was like, oh, you're doing cake.
This is the first time we're going to have, lead author and communicating author in the same podcast. So we're going to learn how to navigate that. That'll be fun. Laudia, we've actually met once before. You spoke at the Roast Summit before me. I remember yes. we actually talked about the paper that we're going to talk, or you talked about the paper you're going to talk about with us today. I didn't get enough time back then to get to know you very well. So I did a little research and I learned that you're from Ghana.
Yes.
Did you do your undergrad in Ghana?
Yes, I went to the University of Ghana in Accra, which is the capital city, and I did a bachelor's in food engineering.
Nice. Do you know where the Guinness Brewery is in Ghana?
Yeah, I interned there actually, the Accra Brewery Limited.
You obviously did very well as an undergrad and end up doing a master's degree already at UC Davis.
Yes.
And I guess you're in the Department of Biological and Agricultural Engineering under the supervision of Irwin Donis, who's also joining us on the call. Before we get to Irwin, I want to ask you another question about this. So obviously you're working in, I guess, agricultural processing broadly defined, but your work is in coffee. And I think coffee is a new focus, well, semi-new focus for UC Davis, let's say in the last 15 years.
Yes.
When you got to UC Davis, were you going there to work on coffee or were you going there to learn about agricultural processing post-harvest, let's say?
When I got here, it wasn't to work in coffee initially. So in 2019, I moved here for my master's, as you said, in biological systems engineering under Dr. Irwin, and he was working on a drying project. So we were looking into using desiccants or drying materials to improve the drying conditions of agricultural products like walnuts, almonds, etc. So as part of my master's project, we decided to use those dry materials to look at how to store or preserve green coffee. So that's when we collaborated with Professor Ristenpart, who's the director of the UC Davis Coffee Center, to look into preservation of moisture in green coffee. So it was more focused on drying. We just ended up applying it to coffee, and now we moved deeper into the coffee side of things.
Was this paper your first time roasting coffee?
Yes, that was the first work we did on the roasting end. Yeah.
How was that experience for you?
Well, I went from having no idea, because in Ghana, we are actually not very big coffee drinkers, even though we do produce quite a lot of coffee. So I went from not knowing much about coffee, not being a coffee person, to like knowing virtually anything that I could find and understanding the roasting process and everything.
In Ghana, coffee's not a popular drink. What is a popular drink?
Actually, we wake up and go straight into the heavy meals. So we have this popular rice and beans meal called wache, which is a very popular morning food, like a street food you buy in the morning.
Straight into the solids.
We're also joined by Professor Donis, who grew up in a country definitely familiar with coffee. So, Irwin, you're joining us here, but you're from Guatemala, is that right?
I am, yes.
And I saw that you were a Fulbright scholar, so you went from undergrad in Guatemala to grad school in Michigan State.
Actually, I went from undergrad in Guatemala to working in coffee. That was my first job after college.
Nice.
I got my undergraduate degree in agricultural engineering.
Mm-hmm.
And, I was working in research, and it was completely different to coffee. I was working in citrus, virus and viroids, and in viroids of coconuts. And I found myself with, having a conversation with a friend that was in the coffee industry. and he was telling me how challenging it was to find certifiers in country for specific certifications related to coffee. Among those, one of them, coffee practices from Starbucks, and that was in the 2004, 2005. I was way over my head. I mean,
I know that feeling. Yeah.
yeah, it was, and not, the time component was impressive. So I had to immediately go to what my job was then in research at the university and tell them, no, I gotta leave, and which I did, and I founded a company with another two friends here in Guatemala, which that company is still alive today. Its name is LATCERT, for Latin American Certification. And yeah, no, before I went to UC Davis, I was working in coffee.
It's pretty cool, first of all, that UC Davis is so broad in thinking, like this like non-traditional way of going through the academic process to bring you into being a high profile scholar, is looking at someone like yourself who trained and then started a business and then went back to being an engineer. I mean, it's remarkable.
Yeah, no, thank you. And it was pure coincidence. Well, none of this was written. The Department of Biological and Agricultural Engineering recruited me as a post-harvest professor in post-harvest comparative extension. So
Yeah.
I was working in many concepts, and ironically speaking, how I got from started with the coffee center is Professor Ristenpart went through my office, and I had a coffee jute bag hanged on the wall. Like you said, I'm from Guatemala. So yeah, when he saw that jute bag, he immediately, I kind of like just went into my office, and that's how I met Professor Ristenpart when the concept of the coffee center was starting.
Yeah. So I like the idea of Bill rummaging around people's offices trying to figure out, he's like, all right, who's going to do something with me?
Who's done an
That's
AeroPress?
Bill. That's exactly Bill. If you ask me, that's how we would define him. Yes.
That's good. Well, so I was reading through your papers and I was thinking, man, this guy likes drying stuff, like big time drying guy. A lot of desiccated materials in your life.
I do. I mean, as a post-harvest engineer, I work in three concepts. Drying is one. The other one is refrigeration or cold storage or the cold chain, and the other one is sensing and post-harvest. In the state of California,
Yeah.
you got to work on drying, man. It's one of those things because we produce, conservatively speaking, 80% of the tree nuts in the world. So we dry a ton. Like we do a lot of drying.
A long time ago, I got to know this guy who was running the seed vault in Svalbard, Norway. And I asked him back then, was coffee in the seed vault? And he told me that no, it won't be ever in the seed vault because I guess when you freeze coffee and then thaw it out, the seed doesn't germinate anymore or something. Is that right?
I have no idea, man. That's a good question.
I didn't know that. And I, evidently no one to this day, us four still do not know it to be true, but he did tell me this. But now, more importantly, I asked him what other seed is not in the seed vault. And he's like, oh man, coconuts. You can't put a coconut in a freezer and then thaw it, and it won't germinate.
We got to do something more sci-fi, like put coffee in like a big cube of jelly or something.
Oh yeah, or coffee in a coconut.
That's another one. Yeah, that's the perfect combination right there.
We're cooking it up right now. This co-ferments where we co-fermented the coffee inside the
The
coconut.
pre-co-ferment.
Yeah, Laudia, you must be almost Dr. Laudia.
Yes, fingers crossed by the end of this year.
Well, first of all, congratulations on that. I went through and had a look. You've published what, like 5, 6 papers now?
Our fourth paper actually just got accepted, also at Scientific Reports. That one is on color during coffee roasting.
Irwin, I got one more question before we get into the paper a little bit. So here, one of the most important things, as you know, in doing good science is having good students. And I want to know, how did you find Laudia?
Laudia came to me. I was very grateful to get an email from Laudia. She was looking for an opportunity. And you know this, Chris, we get hundreds of emails. But
Oh, yes.
yeah, and especially from, students or potential postdocs or whatever. But it's a generic email typically.
Greetings to the day, dear honorable professor.
And you can tell, bam. And I could tell immediately that Laudia did not write a generic email. She worked on it, and that's very telling. And at that point, of course, I had some funds related to the work of desiccant drying. And I figured, okay, let's give it a try. So I basically encouraged Laudia to apply to the graduate program. You know how that goes.
Oh yeah.
And she got accepted and, with flying colors. And I mean, I've been a happy man since then because, I've been lucky enough to surround myself by phenomenal students, Laudia being one of the best. And it's very, eye-opening for me to work with people like Laudia. And it makes my life much more easier.
Yeah, well, I mean, absolutely. Doran's the same for me. It's having a good student around is really helpful. So the paper that we're talking about today was published in the Nature Publishing Group journal Scientific Reports. The title of the paper is "The Effect of Roast Profiles on the Dynamics of Titratable Acidity During Coffee Roasting." This paper came out last year. I've had the fortune of hearing about this in real life at the Roast Summit in Portland, Oregon last year. And since then, the paper's been extremely well covered in the coffee literature, mainstream media, because I think people generally are quite interested in understanding how coffee can be acidic and then taste acidic, that bridge between perceivable acidity and chemical composition. Obviously, the one step that happens in between, when you're tasting it and when the coffee is grown is this roasting process. And so obviously that's where you're going to be generating a lot of the different compounds.
So I want to ask you guys a question. Since we have authors of the paper joining us, usually we talk about a paper and we talk about uh, kind of the context that it exists in the scientific literature, how it relates to the coffee industry, what the results mean, and so on. But because we have the authors on the podcast, could you walk us through the genesis of this paper, kind of how it came about, where the idea came from, and what the intention was for this paper?
Yeah, so taking it back all the way to the beginning, we start this paper or this project is a part of a way larger project where we are looking at how different risk profiles affect physical and chemical parameters during coffee roasting. We started this research in the first place because, in simple terms, coffee lacks research. If you look at scientific databases, how much papers or studies have been done in terms of coffee compared to tea and other commodities, the number of papers that exist in the coffee world is pretty small. And looking at how coffee is like a big commodity, the second traded commodity after crude oil, it needs the scientific work. So we decided to look at what is going on in terms of physical and chemical parameters during roasting. And our overall goal with this project is to build a coffee roasting control chart. I don't know if you're familiar with the brewing control chart.
Yes, we are familiar with the brew control chart, but this is basically just kind of a really rough guideline for ratios and strengths of coffee that tend to taste good.
Yes. So the brewing control chart basically lets you control what is happening in your cup. So by changing some parameters, you can control how your coffee is going to come out, if you'll have more or less body or taste a certain way. So we want to apply that principle to the roasting end of things. Our overall goal is to make a roasting control chart, which lets you control how your coffee will come out of the roaster. So to be able to do all these correlations, the first part was to look at what exactly is happening during roasting, which is why we did this large experiment where we roasted a bunch of coffee and then we measured a lot of physical and chemical parameters, and titratable acidity was the first one that we decided to look at in detail.
Okay, so this is a great answer because this gets at something that most people don't get to see, which is the really big goal. So
Yes.
often in science, we have some really big goal. I mean, in the Hendon Coffee Lab, we're doing all of these electrochemical experiments, and the goal is to make something really useful to the industry. But in order to do that, you need a bunch of small papers first. And so it seems like for UC
Yes.
Davis, the really big goal is finding a way to control roasting in a really specific way. I think a big goal of coffee science, one major thrust of it, is not to replace expertise and craft and the art of roasting. It's to help people understand a little in more detail what's going on so that we can make these small adjustments and make these optimizations and just help coffee become better.
Yes. And I also wanted to add that, sorry, I also wanted to add that there are a lot of common beliefs, especially in the coffee world. So, for example, a lot of people believe that a dark roast has more caffeine than a light roast, for example. So,
Oh, we've
by
we've gotten
doing the
into that.
science and looking, Yes, by doing the science and actually looking at what the data, or by, let's say, studying caffeine dynamics during roasting, for example, we are able to answer these questions so that to see whether these beliefs are true or not, which is also a major thing we are doing with our work.
There are open questions. I think primarily what? Because everyone who roasts coffee is basically an artisan, and they may be scientifically minded and do scientific things, but for the most part, roast profiles are kept as proprietary almost. They're not shared. And maybe they don't need to be shared because we'll get into it. You can have some outcomes that are the same. Like, for example, first crack time can be the same, and there's an infinite number of ways you could get to the first crack, and it will have a different flavor response in each of those different ways. So first thing comes up, I want you to sort of paint the picture here. What is the experiment? What is the central question that we're trying to answer?
Okay. The question we had going in was, what exactly is happening to multiple physical and chemical parameters in coffee during roasting? So to answer this question, we took coffee from 3 different origins and then different processing methods. And then we had washed coffee from Uganda, CP Falls. We had another washed coffee from Indonesia, Sumatra, and we had a honey processed coffee from El Salvador. So with these coffees, we also worked with Timothy Stichinsky, who is a head roaster at Bridge Coffee, to come up or create typical roast profiles in the coffee industry. So these profiles, we have 7 of them, and they range from a fast roast to a slow extended Maillard. So what was different in the differences in roast energy. So for a fast roast, for example, we'll have a high roast energy in the beginning, and as the roast progresses, the rate of rise, which is the change in temperature per 30 seconds, will drop progressively.
Let me ask you a question. I'm going to interrupt you for a second. You're using the word roast energy. What does roast energy mean?
In simple terms, basically how much heat is going into the coffee. And this is controlled by the person doing the roasting.
When we're talking about roast energy, we're not necessarily, so you're not including the rate of tumbling, the energy associated with like mixing the coffee inside the drum. Only the heat, only applied energy, right?
Yes.
So when you're talking about developing these roast profiles, and you said something like a fast roast, fast roast or fast, what are we calling fast start? Excuse me, fast start. A fast start means in effect what? Higher temperature initially?
Yes. So the rate at which the temperature is changing is higher. That's the ROR. If you look at, I think in figure 1 or figure 2, we have the ROR curve, the rate of rise curves in the paper. So you can see that it has a higher ROR at the start.
To give a little bit of context to this, Chris, basically, a fast start, when you drop the coffee, it drops to approximately 100 degrees Celsius. And after just 6 minutes of the coffee being in the drum, we've reached 175 Celsius.
Yeah.
The opposite, the slow start, it takes up to 10 to 11 minutes to reach those 175 Celsius from its initial 100. So it's a much slower, in other words, fast start, you're hitting it with a lot of fire at the beginning, basically.
Okay, but I have a basic question. So I see the dip going to around 100 degrees Celsius, but it seems to be ever so slightly above 100. And this has always been a question I've wondered about. It's like coffee contains, let's say 15%, 10% water. And yet water, of course, liquid water boils at 100. Why is it that I thought thermodynamically you would expect that the minimum that heat transfer would drop? It'd have to go below or to exactly 100 before the bean can start heating up, because there's still water around, so that phase transformation would have to occur. So is it that we're seeing it go above 100 because this probe is not measuring actual bean temperature and it's measuring something near the beans?
Yeah, so on this machine, the probe it's not attached to like a bean, a specific bean. So the temperature you're getting is not the actual bean temperature, like you said. So the beans are tumbling around in there, and it's kind of measuring the average temperature of that enclosure, that space. So we are approximating that to be our bean temperature.
Basically, the reason why this happens, Chris, is cold beans are at around 22 to 25 degrees Celsius. So it's ambient temperature. Okay. The roaster, typically, that's what's stated, at least for industrial scale applications. It's at around between 200 and 225 Celsius. So when we drop at this point, anybody at around 22 to 25 degrees Celsius in that mass of hot air, it is likely going to drop very closely to that around those 100 degrees. Yes.
So imagine if we put in frozen coffee into the roaster, just directly in.
No, that's not true for frozen coffee because then the temperature differential between the temperature of the drum and the temperature of the coffee that is coming into the drum is slightly different. So it's likely going to be lower than 100 degrees Celsius at that point. It's just like that what typically happens with a coffee that is in equilibrium with ambient conditions, which is 25 degrees Celsius.
I see. Maybe the first lesson of the paper, which is that batch to batch treatment of the roaster and of the coffee really matters, because if the initial condition of the roaster is not the same temperature, or if your coffee goes in at a different ambient temperature, you can have a pretty dramatic difference in that initial drop temperature. Laudia, I interrupted you about 2 years ago, so now let's
Yes.
let's get back. So you as a recap, you were telling us that you've got all these different coffees, you're roasting them in different ways, and the basic question that you were trying to answer was what?
Yes, so we have 3 different coffees roasted 7 different ways, and we made each roast 16 minutes, basically going from green coffee all the way to very burnt coffee, because we wanted to look at what is happening in basically. So we have each profile lasted 60 minutes, and at every minute we would take a sample out of the roaster with a sample trier. So what we did was we were interested in what is happening within the roaster and not out of it. So once our samples came out, we put it in liquid nitrogen to immediately cool the sample to stop any further chemical reactions.
Turbo quench.
Yes. So to recap, we have our 3 different coffees roasted 7 different ways, each roast 16 minutes and sampling every minute. So we ended up with around 663 samples. We then took them to the lab and measured about 17 different physical and chemical parameters, including moisture content, color, water activity, and titratable acidity, of course. So we decided to first look at the titratable acidity as a parameter in studying its dynamics during roasting.
So the naive audience member might think, okay, if the thing that you care about is how does acidity change over time,
yes,
you just measure the pH. That's how you measure acidity, right?
Yes.
The next question you might ask is, why don't you just taste it and say if one coffee is more acidic than the other? Can you talk about why acidity in coffee is so complex and how you landed at titratable acidity as the metric by which this paper was built?
Yes, definitely. So we wanted data and our knowledge to help people practically, people in industry, and people tend to measure pH and titratable acidity both measure acidity, and people tend to go for pH because it's easier to measure relatively. For example, the titratable acidity meter that we use in the lab, we had to purchase a $12,000 equipment, and your typical roaster will typically don't have that. So that's why most people gear towards pH. But we decided to go with titratable acidity because studies have shown that titratable acidity correlates better to perceived sourness in coffee as compared to pH, because titratable acidity is a measure of the total acids in the coffee, and pH only measures the strong acids. Coffee, on the other hand, contains both strong and weak acids with more of weak acids. So if you take only pH information, you might not be capturing all of the acids present in the coffee. So titratable acidity is a better measure of the acids that the coffee contain. And also, even though green coffee has 7 to 10% acid content, and there are different acids such as chlorogenic, aliphatic acids like quinic, citric, and malic. And we could measure each of these compounds separately, which is part of our next steps, actually. But measuring the titratable acidity gives you like the total amount of all the acids present, which we believe is an easier thing for a roaster somewhere to do as compared to doing, let's say, an HPLC analysis to look at specific acids. So this is why we focus on titratable acidity.
If you're interested in an HPLC analysis of different acids, you could refer to friend of the lab, Agnese Santanatoglia's studies on acidity in coffee.
Yeah, a plug. There's a plug, an unsolicited plug. Okay, so
are they paying you for this?
Definitely not.
Let me add to something that Doran asked. Like, why don't we use a single panelist, for example, for this, you know, and having a single panelist to assess the samples, and let's say we can ask Tim, hey, Tim, why don't you taste this and tell us which ones are more acid or not, can lead to incredible bias, you know, and this is fairly inaccurate because our tasting buds are very subjective. For 10 panelists, you can already start thinking at 80K or above just to train that panel. Just there. See my point? And an untrained panelist doesn't offer all of the intrinsic details that we are sometimes looking at. So you're at over 200K, man, without anything else right there just to run a sensory evaluation. It's expensive and time consuming.
Just time and money.
Time and a lot of money, you know, sensing require, I mean, it's a lot.
Let's get into how you titrate for acidity. The device that you used is basically an auto titration system.
Yes.
Titrating something is where you add a substance that has a known concentration of one reagent to a system or a substance that has an unknown concentration of something that it will react with. And then you can use simple ratio of how much you added to how much reacted to tell you basically how much unknown material there is. What is the signal that you're detecting? How are you determining when you've measured all of the titratable acidity? Is it done with a color change? Is it done with maybe electrochemically? Like, what is the actual detection?
We used a set point pH of 8.2, which we found in literature to be the set point pH for when titrating brewed coffee. So from getting our samples and taking it to the lab, we brewed our samples with a brew ratio of 18. And then we had an automatic titrator that did this, but basically it slowly added a base. In our case, it was sodium hydroxide, 0.1 molar. And then it slowly added this in drops until it neutralizes all the acids. So how much base it takes represents the volume of base required represented the titratable acidity. So the more base it required, or the more NaOH it required, the higher the titratable acidity of that was. So in our case, it was an endpoint pH, not a color change.
Yeah, that makes sense. So what's implied in that is that all of the acids in coffee have a pKa less than 8.2.
Yes.
I don't want to say it's easy because science is never easy, but in terms of like take a sample, put it in the titrator, push go, and then it gives you a response that says you've got this much acid, actually is a pretty nice way of measuring how much acid is contained within an extraction.
It was straightforward and it was simplified because of the automatic titrator that we were able to get. But again, we had 663 samples. So this did take a while to get through them.
Yeah. I would just make undergrads do all of those.
We did have a team of undergrads working with us in the lab. We had about 7 students we worked with.
Yeah, nice. That's not all they're for.
Which graduate student has 7 undergrads working for her?
Yeah.
You tell me, Chris.
Doran's got 3. I got 4.
There you go. So we beat him by what? By at least 4 with Laudia there. And I think 7 is a little bit in the small side. If we really count everybody that's helped Laudia, we're closer.
7, actually.
Undergrad involvement in research is excellent. So that's great that you've got that number of people who are interested in working with you and that you had that experience of overseeing them and helping them make their, on their journey. Let's go to the extraction part. In order to measure titratable acidity, you're not dropping sodium hydroxide onto a solid coffee bean.
No.
Okay. So you do need to first make coffee. And in order to make the coffee, I guess what's the most reproducible way? I guess full immersion. Is that how you did this?
Yes, we did the full immersion method.
And so you first brew it, some fixed ratio, some fixed time, water temperature is all constant. And we're going to get to the water chemistry in just a second, but let's assume that everything's constant. You dump it out and then you take a measurement of the titratable acidity of those liquids.
Mm-hmm.
I was looking in the supporting information, figure S2, and basically this is looking at when does the coffee extraction process go to equilibrium? That is, when does the total dissolved solids concentration of coffee material no longer change with increasing time? In this process, was the water being heated the entire extraction time?
No, we heat the water in a kettle to, I think it was 96. And then we pour the water with the pour over method with the clever drippers. We pour our water and let it sit for 30 minutes. Remember that we were going for we have samples ranging from green all the way to roasted.
Right.
So if we were to do a typical brewing procedure where, let's say, you do your extraction for 5 minutes, your green sample wouldn't be as extracted as your, let's say, minute 16 or the end of roast sample. So Jessie, who's also a student before me, she did some research where she was looking at how much time it takes for complete extraction to occur. And they measured it by looking at the changes in TDS, or total dissolved solids, over time. And she found that by 30 minutes, whether you have a green coffee sample or you have a very roasted coffee sample, maximum extraction had occurred. So that's why we have those graphs in the supplementary info showing the TDS. We kept measuring the TDS, I think, every 5 minutes.
So let's go to the water then for a second, because I think one of the points I want to make about titratable acidity versus perceived acidity or sourness or whatever, as a panel might assign language to these flavors, is that what you perceive as acidic depends heavily on the amount of bicarbonate that's floating around in the water, because the bicarb is going to react with the weak acids, and the pH won't change because the liquid's buffered, but the acids are still there. They're just now hidden as some other compound, right? And so when you titrate for acidity, you're still able to then detect the acid content, even though you can't necessarily perceive them as acids on your tongue, which is an immensely powerful reason to do titratable acidity measurements rather than sensory panel measurements. Because if you gave the panel this coffee prepared with Pure Life Nestle waters from North America 2019, it might taste a heck of a lot different than one of the second teachings here. If titratable acidity allows you to see the true amount of acid molecules in solution. And so I'm going to give you an item on this. So I did the math for the new version of Water for Coffee that is allegedly coming out at some point in the future. Based on your titratable acidity work that you've done in this paper, I did some quick calculation. And it turns out that there is about 10 times the number of acid molecules as it takes bicarbonate to buffer the flavor of acid almost entirely away in a cup. If you have bicarbonate in there and it is at 1/10 the concentration of the acid, you basically can't taste acid anymore. The lower limits, like super soft water, would have like, 100th of the bicarbonate to acid ratio. It's crazy to think that it's like in that range. But this paper was immensely helpful in me putting numbers on that exact problem of like how much bicarbonate there was. If I'd asked you before this call what you thought the bicarb concentration had to be for you to no longer be able to perceive acid, you probably would have assumed what,
something higher, yeah,
1-to-1, right?
Yeah.
Probably. You would be like, oh, you got to wipe out all the acid, otherwise.
Yeah.
Yeah, but it turns out I think that your tongue is very sensitive to the conjugate base that you would form upon reaction with bicarbonate, more so than it is sensitive to the acid floating around as the weak acid in solution. And so I think that tipping point is something that studies like this one would allow you to really focus in on, because you'd then be able to not only get different acid concentrations, but also then buffer them in different ways, and you could really parse out where it is that's that sweet spot where people start to perceive the acid in a favorable way, but not wipe it all out. Okay, that's the end of that diatribe.
That was very eye-opening. Thank you.
Go back in time for 1 second to extended Maillard. You mentioned that there's this extended Maillard roast profile, and anyone who roasts coffee would look at this and think it's not necessarily what they would do, but it is something that you can do. The roast profile starts out hot. Rate of rise is steadily declining to a point, and then it goes flat. Laudia, tell us about the Maillard reaction, the temperature that you need to be at for it to start, and what extended Maillard means.
There's a common way people call this profile is a baked profile. So I don't know if you've heard someone say the coffee's baked. So it just kind of got stuck in the Maillard phase. So in explaining what extended Maillard means, when roasting starts at around 150 to 170, the breakdown of sugars into brown compounds, which is called melanoidins, which are responsible for the brown pigment or the brown color that we see as the roasting progresses. So this happens around 150 to 170 degrees Celsius. So from your green, your beans begin to lose moisture and they start to yellow, which they start to go into the color change phase, which is where your browning reactions or your Maillard reactions will typically start.
Yeah. Okay. So you're just keeping it in that Maillard zone for as long as possible.
It's like barbecue.
Irwin, is there a product in the market, not necessarily coffee, that people deliberately choose to dry at this temperature to maybe enhance like a umami or a sweetness or something?
Dry at what? At the temperature 150?
Yeah.
No, nothing is right that high. Nothing.
Okay.
The maximum temperatures that we're drying agricultural commodities that I've seen is around 50 degrees Celsius maximum.
Okay.
No, no, I'm lying. I'm lying. Actually, there is some commodity coffee in Brazil that is dried at that temperature. But it's frowned upon because you're basically just burning the coffee, if you may.
Yeah.
You're not keeping any of the flavors. You're basically just doing it for quickness. They're drying coffee lots under the rain in some locations and huge drum dryers, guardiolas, at 150 to 200 degrees in 24 hours.
Yeah, I see. Yeah, so they're basically just
So
roasting the coffee.
basically,
Yeah.
yeah. So no, nothing is dried at that temperature if you want to maintain the quality and palatability of the product. That includes other commodities.
If you were to just grab a coffee roaster by the shoulders and shake them and tell them the really exciting thing that you found in this paper, what would you say?
It would be one sentence, which is you have maximum acidity at first crack during your roast.
You know what? It's so cool to come to a roasters, at least here in Guatemala where I am right now. And they pull out these little sample roasters from their backpacks and they're so excited of roasting all the coffee. And you just approach them and tell them, I can tell you exactly that it doesn't matter what you do, the maximum sourness that you can get is during that first crack. Oh no, Irwin, you're lying. Let's do a test. Go ahead. Roast, come on. Do completely distinct roast, two of them, and you'll see a couple of things that are very consistent. And we can talk about other parameters, but we're specifically talking about titratable acidity. And it's eye-opening to somebody who has been using this sample roaster for the past 20 years, not lying. So that's what's more exciting to me, to be able to pinpoint exactly what's going to happen after certain phases of interest during roasting. And we can pinpoint that now after we've done this measurement.
I can understand why you would see increasing titratable acidity up to a point. And I presume in my mind it would just like keep going up as long as there's compounds you could liberate carboxylic acids from, and whatever the chemistry is that's generating these acids, you could, presumably you'd start to see them. At first crack, it seems no matter which roast profile you use, there's a pretty sharp decline. And that sharp decline is I'd say pretty dramatic, because it's like on the length scale of like tens of seconds. So if you go 10 seconds longer, you can see like you're losing a substantial amount of your titratable acidity. I asked Laudia when I first met you, do you remember the question I asked you about this?
No, the particular one.
I said, where's it going?
Oh yeah, I do remember that. Important.
I'm gonna ask it again. Where's it going?
At very high temperatures, the acids degrade. So the heat degrades the acid. So they decompose or they volatilize.
So they're going out somehow, going out the smokestack or something,
Yes.
Right? Something's happening to them. That is interesting that no matter how you get to first crack, at first crack, the maximum acidity is what it is.
Well, I have a question actually.
Mhm.
Whenever you brew coffee, you're always using a fixed mass, or for the most part, you have a recipe that you follow.
Yeah.
Does the maximum titratable acidity correspond to the highest mass normalized acidity that you can achieve, or is it, if you go like 30 seconds after first crack, you're technically at lower titratable acidity, but the coffee has also lost some mass, and so now there's
Interesting.
maybe in your recipe you actually have more whenever you brew the cup.
That's actually a very interesting question. I'm not sure what would happen.
All right, let's get into my most impactful result according from my reading, and then I'll let you go and you can exist in the world without me in your life. Okay, so I was looking at figure 5, which is neat. This is the one where you overlay the titratable acidity for all the different roast profiles on top of one another, and you have this very nice panel to show the green phase, the color phase, the post first crack, and then the post second crack phase. Okay. And I was looking at this, and the first thing that you might see is that very roughly the maximum titratable acidity roughly for all roasts is the same, roughly. Okay. Plus or minus a little bit. But then I started getting the weeds a little bit, and I started looking at examples where first crack occurred at roughly the same time. Was there a difference in maximum titratable acidity? And so we'll go for the example. This is for the Ugandan coffee. So the extended Maillard for the Ugandan coffee compared to the slow start for the same coffee. You can see that the slow start maximum titratable acidity actually occurs something like a minute after the extended Maillard one does. In other words, the peak of the green and the peak of the blue aren't in exactly the same place, but first crack is more or less in the same place, which is really interesting because that's basically saying how you get to that first crack actually matters more than it perhaps initially looks, when you line them all up on top of one another, because that definitely is a difference. But the more interesting result than that is the one when you look at either the fast start versus EF. What's EF again? Remind me.
Exaggerated flick. So
yeah. That's at the end temperature. You crank it.
Yeah, when there's a fast increase in the rate of rise towards the end. Flick.
So if you look at fast start versus exaggerated flick, or the medium versus PR, which is
production
roast,
production roast. So medium versus production roast. The medium versus production roast, those two maximum titratable acidities basically overlay on top of one another. That's nice. Yeah, and they also they have the same first crack time roughly. That's nice too. But for the fast start versus the exaggerated flick at the end there, you can see that there is actually about, I don't know, let's call it a 10% difference in maximum titratable acidity at that same point. That is an awesome result, because that's the one I would be like hammering on if it were, from my side, because that says to the roaster how you got to that first crack determines the peak acidity that you can achieve. And both the fast start and the exaggerated or extended flick or whatever, both of those are things that people do.
Yeah, which this is like the basis, is what forms the basis of the entire paper, which we are saying that the roast profile, or the way you change the temperature and the time you use in the roast, it does affect all these attributes that you're measuring. For example, if you use a fast start and you stop at minute 8, the titratable acidity that you're recording there will be way higher than, let's say, a slow start that ends also at minute 8. But then if you look at figure 6, we did look at all the peak titratable acidities for each profile and did statistics on them. And we saw that they were not statistically significantly different.
Yeah.
So
that's right. They are the same. They are the same statistically here, but you only did run 3 samples, right? So
we had triplicates for each profile.
Yeah. So for me, I would see that result and say those differences, at least for the triplicates, they're not statistically dissimilar, but I would be like, let's go all in on that 2 data points and let's hammer this as hard as possible, because if it's true that you can tell the artisan that the way that they get to first crack in realistic roast profiles, not the extended Maillard, nobody does that one, but like the other ones.
Yeah.
Oh man, I mean, roasters, this really puts power back to them. It was like, hey, my proprietary roast profile I don't share with anyone. Turns out you wouldn't be able to do anything with it anyway, because you don't know the start temperature of the coffee and all this other stuff that we talked about earlier. But it does mean that it's valuable.
Yeah. So in a nutshell, they can use this to manipulate how sour their coffee comes out.
You've said it. That's the sound bite right there.
Roast control chart.
Yes, definitely.
If titratable acidity does not depend on origin, and it does depend on what you hit first crack, and that's the point where you get the maximum, and they're more or less all the same, why can I not just have one roast profile for all the coffees? Because if they, peak titratable acidity is always the same at first crack, and every coffee responds the same, why do we need different roast profiles?
I think in terms of the origin thing, the 3 origins that we considered, their initial titratable acidity was also pretty similar. They were about 2.5 for each of the 3. But I think if you take, and they were all Arabica coffee. So if you take something like Robusta, for example, which naturally has twice as much acids in it, I can't say for a fact because we didn't do that experiment, but I'm pretty sure it will behave differently, or you might have higher kebs than what we had for the Arabica. So the origin thing was with the condition or the clause that origins did not vary that much in terms of in terms of how much acidity we started with, for example.
I see.
But if you compare Robusta or even a decaf, we don't know how that would we don't know the changes that would occur in those extreme situations.
I see. Yeah. Okay.
And most importantly too, Chris, is we need to remember that this was one measure. Titratable acidity does not define how other compounds are going to change during roasting.
Mm-hmm.
And we know that the flavor of coffee is not only directly related to titratable acidity. You know, this is one important factor, but there's others that ketones, furans, I can think of from the top of my head, even aldehydes and so on that are going to define what's the flavor of that cup.
Yeah. Yeah.
So it's much more complex. The tough part is simplifying, our findings into what we saw right here. But titratable acidity is not only that. That's why, our future research direction is actually what we're doing right now is we're exploring other compounds.
Yeah.
Chemical analysis, we're doing a much more in-depth chemical analysis of the different acids that are either appearing or volatilizing, like Laudia said, like going away. And most importantly, look, to the mice or to my, we're going to have to do conduct some sensory evaluation.
Oh, I thought you were going to say you were going to put the people in the roaster and cook them at different temperatures. No.
That too. Yeah. We'll start with the undergrads.
Yeah, undergrads first. Yeah.
No, but the sensory evaluation, it's really important. It's exactly for what you're saying right now.
Yeah. So much to think about here.
Yeah, we don't do that. We just taste it. And
when you're designing one of these experiments, it's okay to just taste the coffee and say, this is close to something that might exist in the world. And we needn't actually say anything further about like actual high fidelity flavors. I mean, you might for this type of research, but you get the point. It's like when you're doing a roasting thing, you taste the coffee and you say, does this taste like somebody might have roasted it that somewhere else in the world? And if the answer is yes, then you're fine. You just start working, because it's like at the end of the day, like whatever. It's like you can't have a sensory panel do everything. I can't spend $200K in a sensory panel every time I want to do an experiment.
Yeah, it's one of those things, and it's a fine line because whenever we mention anything sensory, look, we had an article right now with Laudia related to color, and it's been accepted to scientific reports too. You're not going to believe what I say right now, but we had 7 reviewers.
That's a lot.
7 reviewers. Basically, Laudia, for the first time in my life, Laudia, the response had a table of content.
Oh, man. Oh. Well, this is what science is supposed to be.
We had 100 comments. We counted and it was like 101 comments to respond to on the paper.
Hopefully they were all, helpful.
There's no chance.
At least 20% of them were helpful.
Oh, that's good.
So 20 comments were helpful. But that said, among these comments, these are the people that don't allow you to publish something if it doesn't have the proper methodology between the sensory evaluation. See my point? So Unfortunately, a lot of times, Chris, we have to avoid that component when we're doing this at this level, but we're thinking about it.
You drop 80K and reviewer 2 says you're an idiot.
Which has happened to me. Though it wouldn't be the first time.
Yeah, me too. That's just part of the job. All right. Well, we've said it all. This has been a lot of fun. Thanks for being patient with Willie here. He's just learning how to podcast at the ripe age of 3 months and 15 days old. So thanks for joining us. Laudia, congratulations on this beautiful work and your progress towards your PhD. We look forward to seeing what you do next. And Irwin, I look forward to seeing you very soon, probably at the next coffee meeting, if not at UC Davis sooner. Enjoy your time, I guess you're in Guatemala right now?
Yeah, we're still working in coffee. I'm here in Guatemala. I'm in a sabbatical till the beginning of September, the beginning of the quarter, fall quarter over there. And then I'm heading back to Davis and continuing to do what we're doing over there.
Well, we look forward to seeing that as well. Thanks for making some time for us today. We really appreciate it.
Thank you very much for having us. This was fun.